Last time we finished with an explanation of the octet rule for ionic bonding. So the octet rule says in stable ionic compounds, each ion tends to have 8 valence electrons. The corollary to that is that metals tend to lose electrons until they've lost all their valence electrons. So for metals, they tend to lose all their valence electrons. And then for nonmetals, they tend to gain until they get 8. So a couple of simple things you need to be able to do with that would be take 2 elements, a metal and a nonmetal, and decide what ratio they're going to combine in. I'm sure you have ample experience with that from your first year in chemistry, but just a quick review. What if I want to combine barium and fluorine? How would I decide what ratio to put them together in? And the answer is decidedly not magic. All right, based on the charge of what ions they would form. So barium has how many valence electrons? So it's going to lose both. So it'll become barium 2 plus. And then fluorine has 7 valence electrons. So it's going to gain 1. So it will make fluorine -1. So if I want to put these two together in a ratio that will work, for every 1 barium, I need 2 fluorides. So putting that all together, I get BaF2. Sometimes you'll have transition metals. With transition metals, there's no simple octet rule. So with transition metals, you need to be told what charge the metal is going to have. So for example, if I have iron 3 plus and oxygen, well, by the same reasoning, I could say oxygen has 6 valence electrons. How many does it need to gain? 2. So oxygen is going to be 2 minus. So if I need to put those two together, what ratio is it going to be? I need 2 irons and 3 oxygens so that I have a balance of positive and negative. So I would get Fe2O3. So that's a skill you should be familiar with from the past. And then naming ionic compounds, we're really not going to talk very much about. This isn't a big part of this course. It may have been a big part of your first chemistry course. But essentially, you name the positive ion, then name the negative ion. So it'll end in IDE. So for the two previous examples, BAF2, we would just call that BA is barium, and F would be fluoride. For Fe2O3, there's just one more thing we need to add in. We need to say what the charge on iron is. So this would be iron, not ion, but iron. Three oxide. So for transition metals, we need a Roman numeral to say what the charge is. And I think that's everything we're going to say about naming. Are there rules about capitalization of the words? In general, the names should not be capitalized. I have seen a lot of people with a misconception that you always capitalize names of chemicals. I think maybe that comes from the fact that the first letter of an elemental symbol is always a capital letter. But no, you should not capitalize these things unless they start a sentence. They're not proper nouns. I wouldn't penalize you if you did, but. All right, so we can use our model of what ionic compounds are like to explain some of their properties. So state of matter. When you think of an ionic compound, what's the quintessential ionic compound you should think of as an example? Salt, sodium chloride. So think of sodium chloride. What state of matter is it? Solid. Ionic compounds are almost always solid at room temperature, and they almost always have very high melting points. What about our model tells us that these things should be solid and have very high melting points? The ions are very strongly attracted to each other, so it should be very hard to pull them apart. And they're also in a very repetitive pattern that usually maximizes that attraction. So you have each positive ion surrounded by negative ions, each negative ion surrounded by positive ions. And in that situation, they are as attracted as they can be. If you change that, it's going to take a lot of energy. Yes, there is no real molecule in ionic compounds. Oh, so the question is, what happens if you do melt them? Do you end up with individual molecules? Do you just and I guess my best understanding would be that if you melt an ionic compound, you just have the ions kind of roaming around near each other in that molten state. So the positives and negatives are still near each other in that case, but a liquid is still a condensed state, so they're still near lots of ions. If you do vaporize an ionic compound, they do form individual pairs usually. But it takes a very high temperature to do that. It's a good question. So the question is, there's a step after that called plasma. I don't want to talk about it right now. A plasma is something you're not likely to encounter in this course. All right, next property, volatility. Does anyone know what the word volatility actually means? All right, you think of explosions, but it's not exactly explosions. Yes, it means how easily it vaporizes. All right, so when you see the word volatility, this is really how easily it vaporizes. And the reason I'm listing this property here is this is one that's listed in the AP objectives. But the truth is, for ionic compounds, they have very, very low volatility. Which means they don't vaporize readily. And that makes sense. You know, you open up a container of salt and you don't smell anything because salt is not traveling from that container to your nose because it's not volatile. All right, conductivity. When you have an ionic compound, each ion is holding on to its own electrons tightly. Electrons can't roam freely. Not like metals. We said metals conduct electricity because electrons roam freely. In an ionic compound, they don't. So electrons are held tightly, so no conductivity. However, if you melt them or dissolve them in water, they will conduct electricity. And in that case, it's not that electrons flow freely, it's that the ions themselves can flow freely. And then the last property would be malleability, or for ionic compounds, lack thereof. What about our model tells us that you shouldn't be able to bend and shape an ionic compound? It's a very rigid model. Again, the placement of ions in that crystal really maximizes their attraction and surrounds positives with negatives and negatives with positives. If you move the crystal around, here's my very simple model of positive negative. If I push on this crystal and slide one layer, then what happens is I now have negative near negative and positive near positive. And so if I push on it enough to slide one layer, now instead of attraction, I have repulsion. And so the crystal is going to break rather than bend. Okay? So moving ions out of place results in repulsion rather than attraction. So they'd break rather than bend. And that's everything I have to say about ionic compounds.